Hi, Algebra 2 Trig students. We are in Unit 5, Lesson 4. We have a warm-up to start off with, so I would encourage you to pause and try this warm-up on your own. All right, so exact form, I subtracted 3, then I had my form right here in exponential form. So how do I deal with exponential form if I want to isolate that exponent? Well, I have to change it into logarithmic form. So my base of 2 is my base of my logarithm. What my value is that exponential is going to equal is the value next to the log base 2. And then, of course, my exponent is what the logarithm is going to equal. So I get log base 2 of 15 equals x minus 7. Move the 7 to the other side. So you can see here, this is our exact form. Now, if we wanted to get an approximate form, I just need to approximate the value of log base 2 of 15. How do I do that? Well, 2 cubed is 8, 2 to the 4th is 16. Since this number is 15 here, then I need to have I need to take 2 to the power of something very close to 4 because 16 is very close to 15. So I am estimated it to be 3.9, and then I add that to 7, so my approximation is 10.9. All right, so what is this last section about? Well, the main focus of this last section in Unit 5 is about graphs of logarithmic functions. So we're going to be looking at what the graph of a logarithm looks like, and then we're going to apply the transformations to it and see how that impacts the logarithmic graph. One of the things, if your teacher hasn't talked to you about it already in class, is that logarithms undo exponents because they are inverses of exponentials. So logs and exponentials are inverses of each other. And if you recall from our definition of inverses earlier this year in the first semester, we can reflect an inverse over the y equals x line, and then when you switch those x and y coordinates or reflect over the y equals x line, you will see the graph of the inverses of each other. They are reflective, they have reflectional symmetry across the y equals x line. So here, if we're going to graph this, I would go ahead and pause. Well, we'll just do it together. Here we laid out some of the ordered pairs already for you, but remember, if anything to the 0 power is 1, so it's rooted here at 0, 1. Then we go to the right side and we stretch it up, whatever that base is, from the asymptote. This is the asymptote right here, horizontal asymptote with this exponential. I have a base of 2. 2 squared is 4, so 1, 2, 3, 4. I stretch up here. 2 to the negative 1 is 1/2, 1/4, etc. So my graph of this exponential is going to look something like this. Okay, now, if the logarithm is the inverse of an exponent and it's reflective across this line, that just means we're simply going to switch the x and y coordinates and graph them. So when x is 1/4, y is -2. When x is 1/2, y is -1. When x is 1, y is 0. So I'm switching these ordered pairs. And now I'm going to graph them. 1/4, I'm going to get -2. 1/2 is -1. 1 is 0. 2, 1. And 4, 2. Now it looks like it's going to come up, and where is my new asymptote going to be? Well, if my original exponential's asymptote was at y equals 0, when I switch x and y, this new asymptote becomes this vertical line, which is x equals 0. The exponential equation's domain is all real numbers. Therefore, when I switch the domain, oh, actually we can't do it yet. Sorry. Oops, I don't know what happened there. So we can't do anything yet because we have to figure out what the range is as well, because x's and y's switch. So what is the range of this exponential? Well, it's going from 0 to infinity. So there's nothing down here in the negative y-axis. The graph is only going upward. So now, because the logarithm is the inverse, we switch the x's and y's, then the domain of the exponential function should be the range of the logarithmic function. And you can see that's true, right? It's going infinitely down and it's going to increase going up and up and up. And then the range of the original exponential function is the domain of the logarithmic function. And you can see that is true from 0 and over, right? Not including 0 because that's where my asymptote is. This is in fact the domain. Okay, next it says observe the graphs of y equals 3 to the x minus 1 plus 2 and y equals log base 3 of x minus 2 plus 1 on the right. Which graph is the exponential function and which graph is the logarithmic function? So first I'm going to look at the graphs and I'm just going to try to identify, is there a horizontal asymptote or a vertical asymptote? Because that's really the key to determining if it's exponential or logarithmic. An exponential function has a horizontal asymptote, as you saw on that previous page. So because my blue graph has a horizontal asymptote, that must be the exponential function. The red graph has a vertical asymptote. You can see it's skimming the line here. It's getting so close it looks like it's part of the line x equals 2, although it's not. Therefore, the red graph is the logarithmic function. Those two functions are inverses of each other because they are reflective over this dotted line, y equals x line. And again, how did I know which graph was which? Well, it's based on the asymptotes, right? So an exponential has a horizontal asymptote and a logarithmic has a vertical asymptote. Now, the next example says these are inverses of each other. Okay, we've seen it graphically. How do we do it graphically? We just switch x and y and regraph those ordered pairs. But how are we going to find the equation algebraically? So here's my original function, f of x equals 5 to the power of x minus 2, and then that quantity minus 1. I want to find the inverse of that function. So we've done this before in the first semester, so you're going to keep it the same process. Step number 1 is to switch your x and y. Remember, this is your y. F of x is the same as y. So I'm going to now make that an x, and my x is now a y. So how do I isolate the y value? Well, first I have to eliminate this one. So I move the minus 1 to the other side by adding. So I'm going to get x plus 1 equals 5 to the power of y minus 2. Remember, I'm trying to isolate this y. That y is an exponent. The only way I can isolate an exponent is to rewrite this exponential form, right? This is exponential form, 5 to the power of y minus 2 equals x plus 1. So I'm going to rewrite the exponential form into logarithmic form. So I have log base what? Well, this is the base of the exponent, so that's the base of my log. So log base 5 of x plus 1 equals y minus 2, right? So remember, it's b to the k equals n. That's the same as log base b of n equals k. So I'm using this rule to change exponential form into logarithmic form. But my last step is to solve for y. So I'm going to move the 2 to the other side. Actually, I'm going to do two things in my last step. One is to change my y into f to the negative 1 of x because I need to use that proper notation. And then my last step is to move this minus 2 to the other side. So I get log base 5 of x plus 1, and I move my minus 2 to the other side by adding 2. So this is the inverse of the original function. The original function is exponential, and its inverse is a logarithmic function. Now we're going to do that same process, but instead of starting with an exponential, we're going to start with a log. So I would pause and try this on your own. Switch the x and y, right? So this is now an x, This is log base 3 of y plus 2 minus 7. So we switched to the x and y, and now I need to resolve for y, and then substitute in f to the negative 1, negative 1 of x for y. So what do? We have logarithmic form. We have log base b of n equal to k. So I need to change that to exponential form. That's my hint. Go ahead and pause and try it on your own. All right, so did you get 3 to the power of x plus 7 minus 2 is my inverse function. So you had to have f to the negative 1 of x, right? What's the first thing I have to do? I have to isolate this log statement. If I don't isolate the log statement, then I can't change it into exponential form. So isolate the log statement first by adding 7. Then I take the base of the log, 3 to the power of x plus 7 equals y plus 2. Move my 2 to the other side by subtracting 2. Change my y to f to the negative 1 of x. Okay, next section, it says, what happens when the base of the logarithm changes? So we just wanted you to kind of have a visual of the impact that changing the base of a logarithm actually has on the graph itself, right? So exponentially, what happened? Well, we see here, we already gave you y equals x to the 2, or sorry, y equals 2 to the x power. And you can see this is the horizontal asymptote, and that base is 2 units above the asymptote. When we move 1 to the right, we go up 2 units. Therefore, what is this blue equation going to be? Well, it goes through 0, 1, and then when you go to the right one, it goes up 3 units. So hopefully you're saying to yourself, that's y equals 3 to the power of x. And then the last one, we go through 0, 1, and when we go to the right 1 unit, we're up here at 8. So hopefully you're saying, oh, that's the base, so that's 8 to the power of x. And the higher the base of the exponent, the tighter the turn, right? The closer it is when you graph to the y-axis, right? So it stretches up more quickly, therefore it has a tighter turn after it goes through 0. So it's closer, those values are closer to the y-axis. The logarithm, right, if we have a base, y equals 2 to the power of x, that's log base 2 of x. Therefore, y equals 3 to the power of x, this blue one here, will be log base 3 of x. And then finally, the green one here, if it's y equals 8 to the x, that's going to be y equals log base 8 of x. Now, what do you notice visually or graphically about your logs? Well, the higher the base, the tighter the turn, so the closer it is to the x-axis, right? So here, with a larger exponential base, we have quicker growth, right? It grows more quickly. Here, the higher the base, the slower the growth. It's going up slower, right? So it turns more tightly toward the x-axis, but it's also slower growth. Here's a smaller base. The y values are getting higher more rapidly. Even a smaller base, y values are getting higher more rapidly. Log function. Now we're going to talk about how to transform, right? So what do these values mean? This a value in front is associated with vertical stretching up or downward, so we call that a vertical dilation. Then you have your base, which is establishing how far you're going to be from your asymptote. This letter C right here is a horizontal dilation. It's stretching it right and left. Then remember your H and your K is kind of your kicking off point. Like that is important. It tells you actually how far you're going to move to the right and left. So this is right and left movement. And then this is, of course, up and down movement. So this is right and left, and the other one's up and down. Kind of from your point where your base is, right? So if it's a minus h, you're going to actually scoot to the right h units. If it's a plus h, you're going to scoot to the left. If it's a plus k, you're going to go up. And if it's a minus k, you're going to go down. So let's look at this first example. Notice that there's no parentheses next to this, so only the x is parenthesized. So that's y equals log base 3 of x plus 2. So my parent function is just log base 3 of x, right? That's your parent function. So this parent function would be log base 7 of x. This parent function would be log base 10 of x. If there's no value there, then it's the common log, which is a log with base 10. If we were going to describe the transformations of this first one, right, there's no a value, there's no c value, there's no h value, there's only a k value. So there's only plus 2. So we're only going to take the original log function and move it up 2 units. So if we move that up 2 units, well, where is the new asymptote? Remember, your original log function has a vertical asymptote. It's the y-axis. It goes through 1, 0. It has a vertical asymptote of x equals 0, excuse me. And so where's my asymptote? Well, if I didn't move right or left any, then my asymptote is still x equals 0. What is my domain and range? Well, all I did was move this function up 2 units, so my domain and range stay the same. So my range is actually from negative infinity to infinity, and my domain is from 0 to infinity. Now the domain and range will change with relation to what? According to what? Well, if you have to shift right or left any, then I'm shifting this vertical asymptote right or left, so that's going to impact my domain. My range is still going to remain all real numbers. Okay, I don't want to give you the answers to the next two. I want you to pause and try these on your own, and then you can check when you're ready. Okay, is this what you got for letter B and letter C? Letter B, we had a vertical dilation. Oops, I don't know why I wrote 2. Sorry, that should have been a 5. So vertical dilation by 5, then we moved right 1. Notice that whatever impact you have horizontally, it impacts, your description of what happens. It also impacts the fact that the vertical asymptote has to move that distance, right or left, and then it also impacts the domain. So here we had a vertical reflection, or reflects over the x-axis. Then we had left 7 and down 5. And the order in which you write those doesn't matter, but when you have left 7, that impacts the vertical asymptote and moves that left 7, so it's x equals negative 7, which also then has an impact on the domain. Okay, example 4, we are going to work on our graphing of a logarithmic function. So we have this f of x. It says f of x equals log base 2 of x plus 3 minus 1. So letter A says identify any horizontal translations and then draw the new y-axis as a vertical asymptote. Well, we can see right here, we're going to have a horizontal translation. It's going to go left 3, right? So if we go left 3, that means my new y-axis is going to be 1, 2, 3. So this is my new y-axis here, which is my vertical asymptote. So my vertical asymptote is at x equals negative 3, right? So if x plus 3 equals 0, this gives you your vertical asymptote. Then it says identify any vertical translations and then lightly draw the new x-axis. So I can see here that I have minus 1, so it's going to go down 1 unit. So now my new x-axis is down 1 unit. Okay, how do I graph the rest of the logarithmic function? Well, we can try to use this table here. I will eventually encourage you not to use a table or discourage you from using a table, but we'll use the table first, and then we'll go back and do it the graph without the table. So one of the things if you're going to use a table is you want to create values that are going to be very helpful when you're taking a log base 2. Like log base 2 of 1 is equal to 0. Log base 2 of 2 is equal to 1 because 2 to the 1 power is 2. Log base 2, so what's another value that might be helpful to take the log of? Well, hopefully you're saying to yourself that would be 4 because 2 squared is 4. Or we could have an 8 because 2 cubed is 8. Now, we want this value how do we get it to become 1? What does our x value need to be in order to make the inside of this parentheses equal to 1? Well, the x value would need to be negative 2. If I plug in a negative 2, I would get log base 2 of negative 2 plus 3 minus 1. Log base 2 of 3 is equal to log base 2 of 1. Log base 2 of 1 is 0. Right, so this becomes 0, and 0 minus 1 is negative 1. So when I plug in negative 2, I'm going to get negative 1. So this is my first point. Next, I'm going to try to get 2 inside this parentheses right here. So log base 2, what plus 3 would give me 2? Well, hopefully you're saying to yourself, if I plug in negative 1, negative 1 plus 3 would give me 2. Log base 2 of 2 is equal to 1, so this becomes 1, and 1 minus 1 is equal to 0. So I'm going to have when x is equal to negative 1, y is equal to 0. So that's another point on the graph. I'm going to do the same thing for log base 2 of 4. I want to get the inside of this parentheses up here, right, to become 4. How do I do that? Well, I make x equal to 1 because 1 plus 3 is 4. And log base 2 of 4 is equal to 2. And 2 minus 1 is equal to 1. So when I plug in a 1 for x, I get a 1 for y. So I go right 1, up 1. That's another point on the graph. And finally, let's do one more. How do I get 8 inside that parentheses? I would plug in a 5. So when x is 5, that would give me log base 2 of 8. And log base 2 of 8 is 3. And 3 minus 1 is 2. So when x is 5, 1, 2, 3, 4, 5. Y would be 2, 1, 2. And so here are the 4 points that I would use. So I'm going to approach the asymptote down here. I'm going to go up through these 4 points. And that would be the graph of the logarithm that was given. Now, why would I discourage you from using the table? Well, that took a long time and it's not really necessary. What you need to know is where the x and y axes meet, your logarithm is going to be rooted one space to the right, because if you want to get log base 2 and get a 1 unit to the right, we need to take that to the 0 power. So 2 to the 0 power is 1 unit away. The base is 2, that's where I'm getting that there. So this answer would be 0. If I want to get this distance, what is this distance? That's 2 units away. Well, that's the base of the log to the first power, 2 to the 1 power. This is 4 units away because that's the base of the log to the second power. This is 8 units away because it's the base of the log to the third power. If I wanted to go down here, guess what this would be? This would be 2 to the negative 1/2, 2 to the negative 1, which is 1/2. That would be a distance of 1/2 units away from the vertical asymptote. So if you take the base of the log and you go up from that new x-axis to the 1 power, 2 power, 3 power, it tells you how far to the right you should move from the vertical asymptote. If you go down and take it to the negative 1 power, etc., because you're going down 1, that again tells you how far to move from the vertical asymptote. And you start right where the x-axis is, 2 to the 0 power is 1, that tells you how many units away to move from the vertical axis. Our domain, as you can see, is -3 to infinity, and our range is -infinity to infinity. If this doesn't make sense, please ask your math teacher. We'll be happy to explain it to you. Okay, here's another question. I would encourage you to pause. Try this on your own. This is a little bit trickier. So we have -x plus 4, or you might want to think of that as negative and then x minus 4. So really, which direction are you moving your vertical asymptote? And hopefully you're saying to yourself, oh, that's to the right 4 units, 1, 2, 3, 4. So this is my vertical asymptote. And this negative sign in front makes me do a horizontal reflection. So instead of having your logarithm open up on the right-hand side, we're going to have it open up on the left-hand side. So I'm going to leave that with you to try to explore right now. And then when you are done, you can come back and check your answer with me. All right, does your graph look like this? So what did we do? Let me just take you through it here. Remember, we said we needed to move to the right 4 units. So this is our new vertical asymptote. So here I got my vertical asymptote by setting whatever was in this parentheses equal to 0. And now I have my new vertical asymptote. Then we talked about the fact that this is a negative in front, and that's a horizontal reflection. So I had to reflect over this vertical asymptote. So now the logarithm should be on the left-hand side instead of the right-hand side. And the rest is just, this is 3 to the 0 power, which is 1 unit away. This is 3 to the 1 power, which is 3 units away. This is 3 to the 2nd power, which is 9 units away. And I'm going to the left instead of the right. I didn't have any shifts upward. I didn't have any stretches. So this is it. We could have used the table. You don't have to. You have your domain and range. All right, example 6, which of the following is a graph of y equals log base 3 of x minus 2 minus 1? So go ahead and have a moment. Notice the scale is counting by 2s. I would pause and try to figure out which one is the answer. And hopefully you got letter B, right? So letter B, because it's a logarithm, and a logarithm means you're going to have a vertical asymptote. So we're immediately eliminating C and D because those have horizontal asymptotes. And then we're going to look at letter A, which has a vertical asymptote at -2. But if we were to take this and set it equal to 0, we would find our vertical asymptote. Our vertical asymptote is at +2. Therefore, it has to be letter B as the solution. Example 7, go ahead and pause and try to come up with this equation on your own, right? One thing you might want to make sure you're recognizing is that this is a vertical asymptote, right? We can see it skimming across that line here. So if that's a vertical asymptote, where is that vertical asymptote? And then you're going to specifically look at this distance here, here, and here. What would that base be to the power of 0, base to the power of 1, base to the power of 2. That helps you figure out your base. So go ahead and answer these questions. And so you can try to figure out on your own. Unpause when you're done. All right, so you should have gotten a horizontal asymptote, a vertical asymptote of x equals 1. Therefore, your h is equal to 1, right? So that's down here. You get x minus 1. You should have gotten a up 3. We moved our x-axis up 3 units. Therefore, our k is equal to 3. So you should have had a plus 3 down here. You should have noticed that this distance is 1. Therefore, there is no stretch value because the base to the 0 power is equal to 1 unit. So that means we didn't have a stretch value. So the base to the 0 power was equal to 1. This is the base to the first power. This is the base to the second power. Now, letter E doesn't say to do this little shortcut method, but you can. Instead, letter E says you should take a point on the graph and substitute it in. So I'm going to demo that for you just so you see it. So if we had our logarithmic equation up here, actually I'm not going to rewrite it. It's right above us here, the f of x equals log base b of x minus 1 plus 3. I'm going to take a point. So I'm going to take this point right here. This point is 1, 2, 3, and then up 4. So I'm going to take this point at 3, 4. I'm going to plug in 3 for x, 4 for y. So y is equal to 4, and then log base b, x is equal to 3. So I'm going to simplify this. Well, how do I simplify? I subtract 3 from both sides. So I get 1 equals log base b, and then 3 minus 1 is 2. This is logarithmic form. I need to change that to exponential form. So this is a base to the power of 1 is equal to 2. So what is my base? My base is equal to 2. So your last step is to substitute in that 2, and then this is your equation of your logarithm. Now, did I have to take that point and plug it in? Absolutely not. I could have seen immediately if there's no stretch value here because it only goes to the right 1 unit, then this is the base, whatever that distance is, because that's the base to the power of 1. So 2 to the power of 1 is 2, so it's 2 units away. You can double check it. This is 1, 2, 3, 4 units away. Well, that's the base to the power of 2, and 2 squared is actually 4. So I would have known the base just by looking at this graph up here, but you could also, of course, plug in a value to calculate it algebraically. So once again, try this again. Let's look at our vertical asymptote. Our vertical asymptote is right here. So go ahead and write your equation. Notice your distance here and here. But the other thing you notice is instead of your logarithm going up, it used to go like this. It has been what? It's been reflected vertically. So make sure you are taking that into account when you are figuring out your A, your B, your H, and your K. So go back through that previous example, read through the instructions if you need help with your H, K, A, and B. Otherwise, pause, try it on your own, and check back in with me. All right, is this what you got for your logarithmic equation? F of x equals negative log base 4 of x plus 2 minus 1. So you can see the base here, 4 to the 0, 4 to the 1, so that's why I have a base of 4. I move to the left 2 units, so that's why I have plus 2. And I move down 1 unit here to get my x and y axes right on this level of this point closest to the asymptote, so that's why I have a minus 1. The one thing you might have forgotten is to include this negative sign in front. Remember, your logarithm is opening, it was a vertical reflection, so you have to be careful. Traditionally, or typically, your logarithm would have opened this way, right? But instead it was reflected vertically, therefore your negative sign goes in front of the log. Now, our next step, our last step, is to graph its inverse and identify the function of the inverse. So algebraically, you're going to calculate the inverse down here, and then make sure you graph it. So how do we graph the inverse? You just switch the ordered pairs, and then we're going to calculate it down here by switching x and y. All right, so let me help you get started. You're going to do x equals negative log of y plus 2 minus 1. So I'm going to switch the x and y, resolve for y, and then I'm going to replace y with f to the negative 1 of x. So go ahead and switch the ordered pairs, graph. So I'll graph that in red, and then go ahead and find the inverse, and then check back with me. All right, this one is a little tricky. So graph the inverse. Well, I switched the ordered pairs. That didn't give me a lot. I was a little stuck here, right? So I just switched -1, -1, that stays the same. This was 2, -2, so I'm going to switch that to -2, 2. Well, that was tricky, right? So what you need to remember is that logarithms and exponentials are inverses of each other. So if I had a logarithm to begin with, when I graph its inverse, it should be an exponential. Now, because of this negative in front, when I solved for my exponential, it has a negative 4 to the power of negative 1 there. So I could have written that as a decay, 1/4 to the power of x plus 1, right? So that would have been the same thing. So that gave me a hint that it has to go down. If there was a vertical asymptote on the logarithmic equation, then there's going to be a horizontal asymptote at the same value. So x equals -2 was my horizontal asymptote. It was decay. I could see that here. It has a base of 4. So when I go 4 to the power 0, It's 1. Then because it's decay, I go to the left. 4 to the power of 1 is 4. So this is 4 units, this is 1 unit, and it goes down. So again, this is tricky, but you can plug in values or just go talk to your teachers. They can explain it a little bit more. Good luck, and come see us if you have questions. Bye.